So today we start with the systems of linear equations. I believe you've had a time to look at the previous topics and hopefully they make sense. Usually if they don't make sense, you should have some questions. If you don't have questions, probably there are two possibilities. Either you have not reviewed the work or maybe it's not making sense. Or you have understood. So if you have questions from the previous one, you can, previous classes, you can ask. Like I said, everything that we have done before, we are going to carry it with us along, even as we go to the applications. That's why we are focusing on the concept first. You get them right, then it will be a smooth sailing when we get to the applications. So here we are. We'll start with this topic, systems of linear equations. So so if we get a finite number of linear equations, so suppose m of them in n variables, then we say that we have an m by n system of linear equations. So maybe I should have given an example of a linear equation here, but this is concrete now. So as an example, these are examples that you have seen before. I think at high school level, this was done, where you had to solve two simultaneous equations. So now here instead of calling them simultaneous equations, we call them systems of linear equations. So this is an example of two equations in two variables. We can have more than two variables. You can have as many variables as you wish. So here is another example with three equations and three variables. So that's a system of linear equations. And you are not limited to what labels you can use for the variables. So when you have very few variables, like 2 or 3, then x and y is fine. But then when we have several variables, we use this subscript notation so that you can list as many variables as you have. So for instance, if you have 50 variables, then using the alphabet will not work because you will run out of letters. You have only 26 of them. Then the other reason you use the subscript, sometimes you need to keep track of the variables. The subscripts help you to keep track of them when performing additional operations on the system or mathematical analysis on the systems. So when you label them like this, it becomes easier to keep track of them. But most of the time, when you have just a few variables, then you don't have to use this subscript notation. So here's an example with a different set of variables, A, B, C, T, and S. I think there's a mistake here. This should be S, but anyway, no problem. Instead of 5, it should be S. Or maybe it's supposed to be 5S. I may have made a typo there. But this is a system of two equations in 5 variables, where the variables are A, B, C, T, and S. So our interest here is to find values of the variables that satisfy all the equations in the system. That is our target. That's what we want to achieve. So equations that look like this are what we call linear equations. Linear simply means the variables are not functions, neither are they raised to some power. They're just as they are, as you see them here. So the next thing we need to understand is when we have a system, what is a solution to the system? So if you have a system of two equations in two variables, a solution would be a list that has two values for x and y. And when substituted into the equation, into the system, they satisfy all the equations in the system. So for instance, we'll figure out how to get a solution. But this is an example of a solution to this system. 1, 1, when x is 1 and y is 1, that should satisfy this. No, so there's a problem here. This should be -2, not -3. So when x is 1 and y is 1, we have 2 plus 3, which is 5. When x is 1 and y is 1, we have 2 minus 4, which is -2, not -3. That should be. I think there's a way. Okay. So you can make that correction. I'll fix it again. I think I'll just note it down and fix when did the recording start? Let me double check. Yeah. It's raining. So with that correction, these values of x and y will give you a solution for this system because they satisfy both equations in the system. So what is interesting about this first system we have looked at, there's only one pair of values for x and y that satisfy the system. So it doesn't have any other solutions. So the next one is a system of two equations in three variables. And here is an example. We'll just double check this so there are no errors. When x is 2, y is 1, and z is 4, those values should satisfy this system. So this is an example of one solution to the system. So let's check. If we have 2 times 2 is 4, 3 times 1 is 3, that's 7, plus 4 times 4 is 16. 16 plus 7 is 23. And this 2 plus 1 is 3. 3 plus 12 is 15. Flip, but we can continue now. So you can hear me?
Yes.
Okay.
Yes.
So these are two possible solutions to the system. You can double check that in your on time later, that these values of x, y, and z actually satisfy this system. So for instance, here, if we use 22 minus 7 and 0, we just plug them back into this system. They should solve the system. I hope that is the case. Now, it turns out that this is a system that has an infinite number of solutions. There are infinitely many triples that will satisfy this system. So that's another alternative. When you have a system of linear equations, it may happen that it has an infinite number of solutions. Here is one example. And in general, any solution for this system can be put in this form, where t is some real number. So if you change the value of t, it doesn't matter which value of t, as long as you fix it, So for instance, if t is 1, then we'll have 5 minus 22. What will that be? Minus 17, I think. Then 2 minus 7 will be minus 5. And then the last one is 0. So that gives you a solution. So any value of t that you plug in here will give you a solution. And there are infinitely many values of t, because t is any real number. So this gives you an infinite number of solutions for this system. Eventually, we shall figure out how to obtain these solutions. The main thing now is to understand a system and a solution to the system, and how you can generate the solutions, or how you can use the solutions. We shall learn how to generate them shortly.
Excuse me, sir.
Yes.
For this particular question, okay, other solutions such as 22, negative 7, and 0, that one works, but I think this format that you've given, 5t minus 22, 2t minus 7, and 0, if you were to substitute 0 in it, you would have minus 22, minus 7, and 0. That is, you substitute 0, t for 0. And that would not match.
So anyway, I think there's an error here. Even the first solution here seems to work. I need to check this. I'm not sure what happened here.
Okay.
There's I need to go through these notes line by line. Even last time, you noticed there were some errors that I had not noticed. But even if you look at this first one, the last value is 4. Which may not be possible to obtain from this, right?
Yes.
But we're about to see some how to find these values. Eventually, you will have them in this parametric form. I'll get the correct ones and put them here. But eventually, you'll have them in this kind of form where you can generate several solutions by simply replacing the values of t. So for now, forget about the accuracy. Focus on the concept. I will have to check this because 2, 1, and 4 seem to work, but they can't fit into this. Though there are times you can split. It may be possible to have what do you call it? Solutions where you fix z to be 0, right? So if you fix z to be 0, this gives you solutions. So there might be solutions where z is not 0 as well, right? So this might give you a partial list of the solutions. So how you get this is by fixing z to be 0, I think. And then you end up with a pair of simultaneous equations in x and y. And then, is that correct? Okay, this will give you a very limited number of solutions. Let's work on the general system. So in general, if you have a system of linear equations, you have 3 options. You can either have a unique solution like the first case we considered. You can have infinitely many solutions like the second case we considered, and you can also have no solution. This last one for no solutions, we did not give an example, but we shall see one shortly. Here's an example. If you work with a 2 by 2 system, unique solution happens when you have 2 lines that intersect. So there are lines that have different gradients. They will definitely intersect at exactly 1 point. That gives you a unique solution. So the second case is where you have infinitely many solutions. In the 2 by 2 systems, what that means is that one equation is just a multiple of the other. and therefore the two lines coincide. So all points on this line will be solutions to this system, because this second equation is just a multiple of the first equation. So they are the same equation essentially. If you rewrite them, it will just be the same equation. For instance, if you make y the subject, you will end up with the same equation in both cases. So this gives you two lines that coincide, and therefore every point on the line will be a solution to this system, giving you infinitely many solutions. So this last one, I made this diagram too small. I think I'll fix that in the LaTeX file. So this gives you two lines which have the same gradient but different intercepts, so they don't intersect. So in such a case, there's no solution because the two lines have no point in common, and therefore you can't find points that satisfy both equations simultaneously. So this gives you an example of a system that has no solution. So when working with larger systems, when you have 4 or more variables, or even 3, it's quite hard to draw. So it makes sense to work with some algebraic techniques to solve them. And so we want to focus on those algebraic techniques that can allow you to work with the larger systems of linear equations.
Excuse me, sir.
Yes.
On the second example that you just gave, how is it possible to have two lines with the same gradient and still they intersect?
The same intercept. You see, when you write a system of equations like 2x minus 3y is equal to 4, this is just an algebraic representation. As algebraic equations, they look different. The algebraic representation is the same, but geometrically they're the same line, right? So they're equivalent. There's some theory I have skipped that would assist you to understand this algebraically. So when working with a system of equations, you can also run some elementary row operations. Now, these elementary row operations on the system do not change the solution of the system. So for instance, you can multiply a row by a scale, an equation by a scalar. In this case, if you multiply this first equation by 3, you will get this second equation. That operation does not change the solutions of the first system. It just gives you a new equation which has exactly the same solutions as the first one. So in this case, these are they are the same, essentially the same equation. If you try to draw this line, it will coincide. These two will coincide. Geometrically, they will be the same line. What you can do is this: try to make y the subject in this first equation, and then try to make y the subject in this second equation. You'll end up with exactly the same equation for the line. You can do that in your own time. So you can just proceed. But basically, the idea behind it is that if you multiply an equation by a scalar, the new equation you obtain has the same solutions as the original one. So there's a lot of theory. If we, I don't know if you want us to go into the theory. So there are two other operations which also don't affect the solutions, and that is the I've mentioned multiplication by a scalar. If you switch the order of the equations, interchange two equations the same way you interchange rows in a matrix, has no impact on the solution. And then if you replace an equation by the sum of itself and a multiple of another equation, again, you get a new equation which has the same solutions as the previous one. So the row operations do not affect the solutions. That's the deeper theory for this. And then the last one, there are two lines that are parallel. They have the same gradient, but different y-intercepts. So they don't meet, and therefore there's no solution. I hope that sheds some light on your question.
Yes, sure.
So we have talked about this. We want to look at some algebraic techniques that can enable us handle larger systems comfortably. So how we shall do this is we shall use the knowledge we have learned from matrices and apply it here. So we'll give the steps that you need to go through to solve. So anytime you have a system of equations, you can write it in matrix form. So you have the matrix which contains the coefficients. Then you have the matrix that contains the variables, in this case, x and y. And then you have the right-hand side vector, which contains the values that are on the right-hand side. So you can put it in vector form like this. So this, you pick this as a vector, and then like that. So there's a different way you can ask this question. The other, if you want to check if this has a solution, the other way to ask the question is to ask if this vector 8, 3 is in the span of these two vectors that make up the columns of the coefficient matrix. But we'll leave that out for now. So we need this coefficient matrix, and then we also need the right-hand side vector. We can drop the vector of the variables and we can recover it later. For now, we just need the coefficient matrix and then the right-hand side vector. So we set up this matrix. This matrix is what we call the augmented matrix. So that's the first step. Pick the coefficients and the right-hand side vector. So the second step is to reduce the coefficient matrix to reduce echelon form. And any operation that you run to do that, you will extend it to the right-hand side vector. So the new system that you end up with will have the same solutions as the original one, but it will be easier to solve. And we can tell, once it is in reduced echelon form, we can tell the nature of a solution, whether they will be unique, infinitely many, or no solutions. So we shall see how that works. So let's run these steps on the system. So the first, this was the augmented matrix we formed earlier. So we need to reduce this coefficient matrix to reduce echelon form. So the first operation we do is to interchange the rows. So because we want the leading entry here to be 1. So instead of dividing this, you could also divide the first one by a half if you wish, or multiply it by a half, not divide by a half. Multiply the first one by a half, you will still get 1 here. You can choose how you want to do it, but we opted to interchange the two rows first. So now we have a leading entry that is 1 here. What's left now is the next step to make this 0. So we find some operation that will do that. The operation is listed here. You have done this before, so I will not go into the details. So this operation will give you this matrix. Hopefully there are no errors. So this is 0. So now you have everything, or almost everything. Now the other problem you need to fix is to make this a 1. You want leading entry in each row to be a 1. So multiply this by half to get 1s. Then the next thing you need to do is to make this make every leading entry the only non-zero entry in its column, so that it's in reduced echelon form. And the operation that does that, the back substitution using this as a pivot, is this one. And you end up with this as your final reduced echelon system. So this gives you a new system of linear equations, which we are going to write out. So the coefficient for the first equation now, the coefficient will be 1 for x and 0 for y. The second equation, the coefficient will be 0 for x and 1 for y. Then the values for the right-hand side will be 2 and 1 as listed there. So this is what we have ended up with. We have converted our initial system of linear equations into this new system. But now from this new system, it's quite easy to read off the solutions. Because this is just 0, it simply means x is 2. This one is also 0. It means y is equal to 1. And the solution now is 2, 1. So this is an example where we have a unique solution. We can check if 2, 1 indeed works for our. So where was the system? So if this is 2 and this is 1, that is 4 plus 4. 2 plus 1 is 3. So luckily this one has no errors. The solution is correct. So does that make sense? So the plan is this. Pardon?
Excuse me?
Yes.
Someone is requesting to be let in.
Okay. Let me do that. I keep forgetting to do some research on how to make someone else admin. Actually, there are quite a number who are in the lobby. But these ones are the latecomers, I think. Now we are 40. The number keeps reducing as the weeks go by. So I think anyone who was in the lobby is now in the meeting, I think. Okay, we can resume the slides. So far, I think no one seems to have a question on this. It seems to make sense. But the basic idea is this: you set up this augmented matrix, then convert this coefficient matrix into reduced echelon form, and any operation that you run on this matrix, you also run on the right-hand side until this coefficient matrix is in reduced echelon form. And when it's in that form, you can easily read off your answers from the final system. So when you have a unique solution, then you just read off the answers from that final system. So this final system, again, is built using those raw operations that I mentioned earlier. And the raw operations, as mentioned, also do not affect the solution. So let's look at something a little more interesting. So here we have a system of 3 equations in 4 variables. So the first step is to set up the matrix. I hope. Anyway, focus on the process. Hopefully there are no errors in this one. I have not double checked. If there are, we shall fix them later. For now, focus on the process. So the idea now is to convert this coefficient matrix into reduced echelon form. The first 2 operations that we run are given here. And we end up with this as our first step in the matrix. Then, and remember, like this operation, the target is the coefficient matrix, but it also is run on the right-hand side vector. So you can make the leading coefficient in the second row 1 multiplied by 1/5. The operations that are used are given here. The other one also is -1 here. You can make it 1. So now we have all the leading entries in each row being equal to 1. The only thing left is to make each of them the only non-zero row in their column. So So we start with this one. So when you are now trying to turn them into reduced echelon form, you use back substitution. So you start with the lowest leading entry as your pivot. So using this as our pivot, we can make this 0 and this one 0 as well. These two operations are the ones that give us that the desired form. So we have 1 0 0. What's left now is to turn this into a 0. The operation that will give us that is this operation. You replace the first row by the sum of itself and -1 times the second row. Then you have a 0 here. The others you can double check that they work. This gives you the other values that you need. So now our right hand side, this matrix, the coefficient matrix has been reduced to, it's now in reduced echelon form. We can rewrite this as a system of linear equations. Now this new system of linear equations is algebraically it's different from the initial system, but it has exactly the same solutions as the initial system. And we shall use that to our advantage. So this is now the system written out. In the first equation, the coefficient of x2 and x3 are 0. In the second equation, the coefficients of x1 and x3 are 0. And in the last equation, the coefficients of x1 and x2 are 0. You can tell that from the matrix here. There are these zeros, these two zeros, and these two zeros. So we rewrite with that in mind. So the difference here is now we cannot read off because we have a small problem. There are these values for x4, which were not 0. And we couldn't zero them out because the x4, this column does not have any leading entry. So we couldn't zero them out. So now we have to bring in some new terms. So you look at each variable, any variable that corresponds to a leading entry when the system is in reduced echelon form will be called basic variables. So if you go back to your reduced echelon form, this is a column for variable x1, and there is a leading entry in that column. So x1 becomes a basic variable. This is a column for variable 2. There is a leading entry in there, in that column. So x2 qualifies as a basic variable. The same happens to x3. x3 is also a basic variable. x4 does not correspond to any leading entry. These are all the leading entries you have because there are only 3 rows. You can only have three leading entries. x4 does not correspond to a leading entry, so it doesn't qualify as a basic variable, but we can give it a different name and we'll call it a free variable. In some books, they may call it a non-basic variable, but we shall call it a free variable. And that is what we shall call any variable that does not correspond to a leading entry. So x4 is the only free variable. Now to solve this system, what you need to do is to rename the free variable, give it a label, or before we give it a label, we can just rewrite all the basic variables in terms of the free variable. So x1, x2, and x3 can be written in terms of x4. We just shift the values to the right-hand side and express x1, x2, and x3 in terms of x4. So that's what we've done here. I hope there are no errors on this one now. So when you make x1 the subject in the first equation, this is what you get. Do the same for x2 and x3. This is what you have. So now you have a solution. The only thing you need to figure out is what to do with this x4 now. So what we do without x4 is we give it a label. And then we can write out our solutions as follows, where the value of x, if we call x4 t, then anywhere I have x4, I can replace it with t. And that's what I end up with here. So my x1 will take this value. X2 will take this value, X3 will take this value, and X4 was labeled T. So this gives me my solution to the system of linear equations. If I want a particular solution, I just need to fix the value of T. So if I fix T to be 0, I will get a solution. If I fix T to be 0.5, I get another solution. And any other value of T I wish to, I fix into this, it will give me a solution. So that means this system has infinitely many solutions. All I have to do to get a solution is to substitute a value of T into each of these expressions. So I think we have some examples where we've done the substitution here. If if T is 0, then this is a solution. If T is 1, this is that, okay, you can work this out yourself. What is 8 minus 22? Is it 14? So on. So when T is 1, you just come back to this, make your substitution, and you will have a solution. And any value of T that you plug in here will give you a solution. So that tells you that this system has infinitely many solutions. So the basic idea was the same as when we worked out the case where there was a unique solution. But the difference is where there was a unique solution, there were no free variables. All the variables were basic. So we didn't have to express the basic variables in terms of the free variables because there are no free variables. All the variables we had in this case corresponded to leading entries in our reduced echelon form for the matrix. But this second one, in the reduced echelon form, you can see that only 3 variables out of the 4 correspond to leading entries, and those turn out to be the only basic variables. Then you have the non-basic, which was X4 in our case, and you have to write all the basic variables in terms of the free variable. In this case, there's only one free variable. You can have more than one free variable depending on the system. I didn't put an example where there's more than one free variable, but I think I can give an exercise where that happens. Or maybe add one more example before I share the slides. So this gives an example where you have infinitely many solutions. Is that making sense?
Yes.
So we shall do this in Python also. So you will be able to do small examples by hand. You are expected to be able to do these small examples by hand, but for larger systems, we shall run them in Python later. You will see. Basic idea is for you to understand what is going on behind the scenes now, so that when we are running the systems in the software, you do not have black boxes. It's not a black box kind of approach where you don't know what is going on behind the scenes. So this is what I mentioned earlier. Once you have your system in this reduced echelon form, during this process of solving, if all the variables are basic, then you'll have a unique solution. If at least one variable is a free variable, then the system will have an infinite number of solutions. If you have a row, if in the process of row reduction, you end up with a row of this form, where all the entries on the left-hand side are 0, and the one on the right-hand side is a non-zero value. If such a row occurs, then your system will not have any, will not have a solution. So this is quite common, this kind of situation, and in such situations is where you may use some approximate solution to the system. We'll learn about that later. What we call least squares gives you the approximate solution. So we might do that next week. Are these making sense?
Yes.
So to solve this, if you have a coefficient matrix like this, which is invertible, if you have a system of linear equations and you have a coefficient matrix which is invertible, it's possible to solve the system as follows. You simply get the inverse of a coefficient matrix. So, but the theory is here. If you write the equation in matrix form, you have A, then you have a vector X representing the variables, and then the right-hand side vector, we call it B. So if you multiply both sides on the right-hand side, on the left-hand side of both sides, you multiply by the inverse of the coefficient matrix, then you end up with X, the solution as A inverse, multiplied by B. So you have the variables, the vector with the variables, and on this other side, you have the computation that gives you the values. Now, this only works if your coefficient matrix is a square and it's matrix and it's invertible. Doesn't work with any other situation. Your matrix must be invertible for this to work. If it's not invertible, you can't use this. So this is limited to invertible matrices. So we can check the inverse of A is this. So if you want to get, there should be an equal sign here between these two. XY is equal to, so there's a missing equal sign. We'll fix that. You multiply the inverse by the vector to get the answer. So the value of X is 1, and the value of Y is 2. So this can work even for any square matrix as long as it's invertible. If it's invertible, you can do this. I just use a small example to illustrate. I don't know if this is a good time to take a break or we continue. We're about to go to a new topic. So we have checked two ways of solving systems of linear equations. We have looked at the row reduction, which is called the Gauss-Jordan elimination. And then there's this case where the coefficient matrix is invertible. Then you can solve it using the inverse. There are a few other techniques as well. There is this inverse technique is equivalent to, what is that other system called? Cramer's rule. They're basically the same, but we don't need Cramer's rule for most of what we want to do, but it's easily available. If you want to read it, it's available in most books, most linear algebra books. I should share a linear algebra book where you can get those details. I shared a book that's called Matrix Methods in Data Mining and Pattern Recognition. I think I shared with the Kibet. Hopefully all of you have now have a copy. That book is a bit advanced. I have watered down the material. It's essentially teaching you numerical linear algebra. I don't know if any of you have had a chance to look at it. Ideally, that is the level at which we are supposed to work. But if I put it at that level, probably it will be challenging for half a good chunk of the class. And the thrust of this is to get just what you can use to apply, but still have some theory with you. So I've kept it. That's the theme I've kept for this class. But as time goes by, we might pick one of those advanced topics and try to deal with it at that level, so that you get to see how you handle the advanced topics. But we shall not keep every one of them at advanced level. So the question is, have you gotten the book? Is there anyone who has not gotten the book? Yeah. Have you tried to read it, or you have just put it as a decoration? How do you find the book? No feedback. Ama bado hamjafungua.
We have tried to read it. It's a little bit challenging, but
Yes.
interesting.
Yes. That is where the good stuff is. When you find the challenging things, that's where the good stuff is.
Okay.
What I'm teaching is not the good stuff. It's what do you call it? Is a term.
Interesting.
No, this is not interesting. This is I've forgotten the term I wanted to use. If I remember it, I will say it. But just follow what you're doing in class now is going to be useful when we start the application. So make sure you master it. There's some videos on YouTube from MIT by Gilbert Strang. If you want some more detail, you can watch those. I can share the link, the MIT videos on linear algebra. I have not gotten feedback whether you want a break or not, so I think I'll assume you don't want a break.
Excuse me, sir.
Huh?
Let's have the break.
You take the break now.
Yes.
So 10 minutes?
Yes. 7:35.
Okay. So we'll. You want to steal 2 minutes? That will be 12. So anyway, we can resume at 7:45. Is that okay?
Yes. She.
Hmm? Okay. I'm going to do for you for.
Yeah, today they had literacy.
Ma'am, yes,
See what did you do in literacy?
I do for literacy. I do for literacy for eating lunch.
What did you eat for lunch?
Today I eat for lunch.
So we can continue.
Yes.
So the next topic is eigenvalues and eigenvector. So we have to make some demands on the matrices here first. We need the matrix to be a square matrix. And also we need a non-zero vector V and a scalar lambda such that AV is the same as lambda V. So keep that in mind. It must be a non-zero vector which satisfies this condition. So A is a square matrix, V is some vector multiplied by A. It's the same as multiplying the same vector by just a number. So in this situation, this vector V is called an eigenvector for the matrix A, and the lambda is a corresponding eigenvalue for the matrix. So they come as a pair in pairs, an eigenvector and the corresponding eigenvalue. So our task will be to, given a matrix, our task will be to find these eigenvalues and eigenvectors. So we look at some examples that have been worked, they're sort of rigged in some sense. They are set to work. If you have this matrix A, then and this vector 1, 1. If you multiply A by this vector, you get 3, 3. But this resulting vector is simply a scalar multiple of 1, 1. It's 3 multiplied by 1, 1. So this matrix acting on this vector turns out to be the same as simply multiplying that vector by this number 3. So this number 3 is what we call the eigenvalue, or an eigenvalue, not necessarily there. It's an eigenvalue of this matrix. And there's an eigenvector as well corresponding to that eigenvalue. So this is one of the eigenvectors, and the corresponding eigenvalue is 3. So here is another example. You have this matrix, and this turns out to be an eigenvector. Because if you multiply this matrix by this vector, it's the same thing as multiplying that vector by a number, and that number is -5. So -5 is an eigenvalue, and this is a 1, -2 is a corresponding eigenvector. So that's an example of 2 by 2 again. You can also see some examples of 3 by 3 matrix. So we have this matrix. This is an eigenvector corresponding to the eigenvalue -2. This one is an eigenvector corresponding to the eigenvalue 4. I think someone is trying to join and admit them. So this gives you a rough idea of eigenvectors and eigenvalues. So the next step is to figure out how do we compute them. Is that making sense? In this case, the eigenvalues and eigenvectors have just been dropped from the sky, so we don't know how they came about, but we're about to figure that out shortly. So is it making sense so far? Is there anyone who is not following? So suppose we have a square matrix A. This is the procedure that we will use to compute the eigenvalues and eigenvectors. It's quite involving, so you have to pay attention and keep track of it. So the first thing is you construct this matrix A minus some scalar lambda multiplied by the identity matrix of the same size as A. So the identity matrix is a n by n identity matrix. A is a square matrix of size n by n. We subtract this scalar multiple of I from the matrix A. So we construct this new matrix first. Once we construct it, we find the determinant. So I don't know what notation did we use for the determinant. There are two notations. You could use the short form DET, the first 3 letters of a determinant, to denote the determinant of a matrix. But another way to do it is to put 2 straight bars around the matrix. When you have 2 straight bars around the matrix, that means the determinant of that matrix. So you can use those 2 notations interchangeably. Once you construct this matrix, you have to compute its determinant. Remember, you have some unknown lambda in this evaluation. This expression has some unknown value. So the determinant will be a polynomial in that unknown value lambda. So once you have that, it's called a characteristic polynomial. Once you have it, you will be able to find the roots of that characteristic polynomial. And those roots are what you call the eigenvalues of A. Now, once you have the eigenvalues, you can compute the corresponding eigenvectors by solving the system of linear equations whose coefficient matrix is this A minus lambda I, the same matrix that you got here. So you would have to keep shifting the value of lambda, and then you solve the system using that value of lambda to get the corresponding eigenvector. So these are the steps that we shall be using to compute the eigenvalues and eigenvectors. If there are no questions, we can look at an example. So this one says find the eigenvalues and eigenvectors of this matrix A. Remember, there are several steps. The first step is to get this difference, A minus lambda multiplied by the corresponding identity matrix. So if you multiply lambda by the 2 by 2 identity matrix, this is what you get. If you subtract it from A, this is what you get. If you get the determinant now of this 2 by 2 matrix, it will be a polynomial of degree 2 in lambda, which you can factorize as lambda plus 5 and lambda minus 2. So once you factorize the polynomial, you can get the roots. The roots are the values for which the polynomial is equal to 0. So that will be lambda is equal to -5 and lambda is equal to 2. So those two become your eigen values for this matrix. Now, for each of the eigenvalues, you need to compute the eigenvectors. We shall do each separately. So this, you have to create, for each value of lambda that you obtain, you have to create this matrix. In this case, it's the lambda is -5. So we just make that substitution here in this expression. And when you do that, your answer is this. You can go back and do this by hand. So you have A minus 5I. If we go back a few steps, it will be A minus, not 5I, it's minus -5 times I. Let's just be sure that that is correct. So since you have a double negative, you'll end up with a plus. So this will be a 5 and a 5. If you subtract 1 minus 5, you should get -4. Then minus 4. No, it's 1. Since it was a double negative, so you have plus, sorry. 1 plus 5 should give you 6 for this first. 3 plus 0 will give you 0. 2 plus 0 will give you 0. And minus 4 plus 5 will give you, is it 1? Yes, so this is what you end up with. So now this, once you compute this becomes your coefficient matrix for this system of linear equations. Now, this system assumes we have 0, the 0 vector as your right-hand side vector. So these ones will always be 0 for this case. You set them up as 0. Then you have your system now in the augmented matrix form. You reduce the right-hand side to reduced echelon form. And this is where you end up. So anytime you're doing this, solving a system of linear equations, if you end up with a 0 row, you can ignore that 0 row. So here, remember, we said when you have a system like this, you have to identify the basic variables and the free variables. The basic variable in this case is x, because this column that corresponds to the x variable, there's a leading entry. Y is not a free variable. It is not a basic variable because if you go to the column of y, there's no leading entry. So y is your free variable. Now you have to write your basic variable in terms of your free variable. So we give the free variable a label. In this case, the label is t. So xy will be equal to -12 t. So this gives you the eigenvectors. Any eigenvector of this form already vector of this form will be an eigenvector corresponding to the eigenvalue minus 5. So we can fix a value of t to give us a specific value of the eigenvector. Depending on, if you don't want to deal with fractions, you could multiply throughout by 2. If you multiply this by 2, you will get -1 and 2. You get rid of the fractions. So any multiple of this will be an eigenvector corresponding to the eigenvalue -5. So, but since we want a specific vector, if you want a specific vector, you just fix a value of t, and that will work. It doesn't matter what value of t you pick, your answer will be an eigenvector. Is that okay?
Yes.
Good. So this gives us an eigenvector. So there are several different answers you can give. You just need to fix a value of t. Any of those will give you a correct answer for this eigenvector. So, but we picked t is equal to 1, and then we ended up with this as our eigenvector. So we still have one more eigenvalue. That is when lambda is 2. Again, we create this coefficient matrix. Then we have to solve this system. Remember, it has to be this system where the right-hand side is all zeros is called a homogeneous system. So we get the augmented matrix, do our magic, and we end up with the reduced echelon form here. Just give me a minute. So we end up with the reduced echelon form here. We have 1, then we have 3. The second row is all zeros, so we can ignore it. We don't need it anymore. Our basic variable is x. Our free variable is y. We write the basic variable in terms of a free variable. So we set y to be t, and we're able to write x, both x and y in terms of t now. T as a label. We can pull out t, then we have 3, 1. 3, 1 is our, any multiple of 3, 1 now will give you an eigenvector corresponding to -2. So for a given eigenvector, eigenvalue, you can have several different eigenvectors that work. So these multiples of 3, 1, any one of them will give us an eigenvector. So we fix t to be 1, and we're able to get an eigenvector that corresponds to the eigenvalue -2. So as a remark to emphasize what I was saying here is if you have an eigenvector corresponding to a given eigenvalue, then any scalar multiple of the same eigenvector will also correspond to the same eigenvalue. It will work. If you plug it into if you multiply it by the matrix, it will work. You will see that it works. You should try it yourself. So try this with different values of t and confirm that in any of those cases that you try, the corresponding eigenvalue will be -2. So you can do this for a larger system. You can go up to 3 by 3, any square matrix. You can do this and solve this. An example here of a 3 by 3 matrix, but maybe I can add one before I release the slides. So the next topic we shall look at is diagonalization. So if you have a square matrix A, and suppose that the square matrix has exactly, it's of size n by n and also has n distinct eigenvectors. There are situations where you have an n by n matrix, but it has the number of distinct eigenvectors will be less than n. In this case, we insist that they should be exactly n, the number of distinct eigenvectors. Of course, they cannot exceed n because you have a polynomial of degree n. So the number of roots cannot exceed n, and the number of eigenvectors correspond to the eigenvalues, and therefore they can also not exceed n. But we want a special case where they are exactly n distinct eigenvectors. So we can create another matrix which we call P, and this matrix will be the matrix whose columns are the eigenvectors of A. We can also create another matrix D. This will be a diagonal matrix, and the diagonal of this matrix D will be the eigenvalues of the matrix A. The eigenvalues will be in the order of the columns as they appear in the matrix P. The order must be maintained. So if that is the case, if you can, once this is done, then we say that the matrix A is diagonalizable. But that is only if n has distinct, if the matrix A has n distinct eigenvectors, that's when this is possible. It's not possible for all matrices. It's possible for only those that have n distinct eigenvectors. So we have started, we are now moving into the world of matrix decomposition. There are a few other this is called the eigen decomposition of a matrix, and it's not possible for all square matrices. So we will look at other decompositions which are they can work for any square matrix, or in fact, there are some that can work for any matrix, whether it's square or not. We shall look at those later. In particular, the singular value decomposition will work for a matrix that is not square, and square ones as well. It works for all matrices. So it will overcome this limitation for this eigen decomposition. So this process of finding the matrix D such that A can be written as this product is called diagonalization. So it's the special case where the matrix is symmetric. Remember, matrix is symmetric if it is equal to its transpose. If a matrix is symmetric, then it makes your work a bit easier. It's possible to find an orthogonal matrix P, which diagonalizes A. So orthogonal matrix makes your work easier because the inverse of an orthogonal matrix will just be its transpose. Once you have the matrix, all you have to do to get the inverse is get its transpose. Then your work becomes easy. So this diagonalization is useful for a few things. Some applications. One application is getting powers of matrices. So I will add that application. If you can diagonalize a matrix, then it's easy to get any power of the matrix with this diagonalization. So that now can be applied to things like Markov chains, where you sometimes have to get a relatively high powers of a matrix. You can apply it to population dynamics. There's some applications you can do this for differential equations as well, systems of differential equations. It's useful in solving those systems. We will not look at those now. So it gets better when you have a symmetric matrix, and only when you have a symmetric matrix is it possible to have this diagonalization where the matrix P is orthogonal. So this last step, it's a sentence, but for some reason, it's all one word. So this factorization, this matrix factorization turns out to be very useful in applications. We shall see as we go along. So we look at an example. I think this is a matrix we worked with earlier. So we have the matrix here, which we already found the eigenvectors to be these two vectors, -12 1 and 3 1. Let's admit some people in the room, then we continue. So we had computed this earlier. So we know that these are the eigenvectors. Remember, you could use this or any multiples of these vectors. Any of those will still work. So we need to create the matrix P. How do we create the matrix P? We take these eigenvectors as a columns. So we pick this as our first column, then this as our second column. Then we can compute the inverse of P. So P inverse is this. And we can get the diagonal matrix D, which is this matrix where the diagonal is just consists of the eigenvalues. Now the order of the eigenvalues is important. The first eigenvalue you put here must correspond to the first eigenvector in your list. And the second eigenvalue here must correspond to the second eigenvector. Now, if you change the order of these eigenvectors, then you have to change the order of the eigenvalues as well in this diagonal matrix. So now we have all the matrices we need to decompose A. So if I multiply these three matrices, I should recover A. This was the matrix A. So the important thing is to get the eigenvectors, construct this matrix P. Once you have the matrix P, you can compute its inverse. And by then, when you're working this out, you would have gotten the eigenvalues as well. You can put them as a diagonal in this matrix T. So now if you multiply these, you will get the you will recover your original matrix A. So we have just used a matrix that whose eigenvalues and eigenvectors we already computed before. Is this making sense? So the next thing we'll look at is when A is a symmetric matrix, then we can always find a matrix P that is orthogonal. So this time we pick a 3 by 3 matrix A. So we can confirm that A is a symmetric matrix because it is equal to its transpose. So the first thing to do is to find the eigenvalues of the matrix A. Remember, you have to compute the determinant of this expression, A minus lambda times the identity matrix of the same size as A. So that's here. So this matrix is what we have. A minus lambda I is equal to this matrix. Now we need to compute the determinant of this matrix to get the characteristic polynomial. So next step would be to compute the determinant of this matrix. If you work it out, you get a polynomial of degree 3. And the roots of that polynomial are 6, 3, and 0. So these are the eigenvalues of our matrix A. So I think you must have learned how to get roots of polynomials in undergraduate. So this is what we have as the roots. Are we together? So now we have eigenvalues. We need to find the corresponding eigenvectors. So we shall have for each eigenvalue, we will have to construct a system, a homogeneous system of linear equations to solve using this as a coefficient matrix and substituting lambda for each of these values. So that's what this step says. You need to solve this system where A minus lambda I is the coefficient matrix of your system. So for lambda is equal to 6, you can solve it, and we will not go through the full solution. Remember, you make this an augmented matrix, then the right-hand side vector will be the 0 vector. You have a homogeneous system, then you solve it, and you can pick a specific vector or any multiple of it as your eigenvector. So this will be the one of the possible eigenvectors corresponding to the eigenvalue 6. When lambda is 3, A minus 3I will be equal to this. You can set up a system of linear equations with this as your coefficient matrix, and the right-hand side, all zeros. And when you solve it, this is what you may get. You can get a slightly different vector from this one, but it will be a multiple of this, most likely. That gives you the vector corresponding to the eigenvalue 3. And here we get the eigenvector corresponding to the eigenvalue 0. So we have all the 3 eigenvectors. We can construct the matrix P. But before we do that, remember, we want to do orthogonal diagonalization. So before we do that, we are going to turn all these vectors into unit vectors. To turn the vectors into unit vectors, we simply multiply them by a scalar. And as we had seen earlier, multiplication by a scalar does not affect the property of being an eigenvector. It still remains an eigenvector if you multiply it by a scalar. But this will give us, if we make this an orthonormal vector, or rather unit vector. Make this a unit vector, it will still be an eigenvalue. I mean, an eigenvector. So we do that for all of them. Turn all of them into unit vectors. Simply divide them by the or divide them by their magnitude, and you will have unit vectors as your eigenvectors. So another thing that we'll point out, we didn't go into the theory. You will notice that V1 and V2 are orthogonal. Is that correct? They're supposed to be orthogonal. If they are not, then it's possible there's a mistake. We shall double check later, but they are supposed to be, if they are vectors that correspond to distinct eigen values, are supposed to be orthogonal for this symmetric matrix. So there may be an error here because V1 is not orthogonal to V2. Times 1. So what's going on? I'll double check this, but let's work with the assumption that they're correct now. There may be a problem with these ones. The dot product is supposed to give you 0. Pairwise, you look at them pairwise, they're supposed to give you 0. Let's check this last one. These last two. This one and this one are orthogonal. This one and this one don't seem to be orthogonal. So there might be a problem somewhere. I'll check it. So, but assuming that everything was done correctly, once you normalize them, you turn them into unit vectors. Now you take this as your eigenvectors corresponding to the 3 eigenvalues. All you have done is multiply them by a scalar, so they don't lose the property of being an eigenvector. So you pick those eigenvectors that have been normalized and use them as the columns of your matrix P. Now, if everything has been worked out correctly, this matrix is supposed to be orthogonal so that its inverse is just the transpose. And the matrix with the eigenvalues, the diagonal matrix with the eigenvalues on the leading diagonal becomes your matrix D. Remember, the order in which these values are must correspond to the order of these eigen vectors. If you change this order, you must change the order of the eigenvalues as well. So assuming our calculations are correct, then this should be the inverse of P, the transpose, because if they are correct, then this matrix will be orthogonal. So its inverse is just the transpose. And then you can apply this decomposition, and A will be equal to P D P transpose. So I will have to double check these eigenvectors, especially the first one. So this gives you the orthogonal diagonalization of the matrix A. So that's the last thing we are doing for today. If there are no questions, we can stop there. We'll try to share the recording by tomorrow, or maybe even today, depending on a few things. Then I will clean up the possible errors, especially this last calculation. And I think the very first one we did seem to have an error as well. I will run through it and fix it. So all this stuff we'll be doing, we shall run it in Python also. So you will get the rich man's way of doing it. Rich man can buy the software and or get the software to do it for them. So we shall look at that as well. For now, you just need to get the ideas, understand the concepts, so that when we go to application, you don't have any gray areas. Does this make sense? Am I the only one in class, or you are not responding?
Yes, it is.
So Ayub, I think, is a spokesman for everyone. Ayub says it's okay.
Hoping that everyone is fine also.
So you are putting a disclaimer.
Yes.
Okay.
Yes.
So again, what I've put here is very simplified. There's a lot more behind this. There are other things you can talk about when we're talking about eigenvalues, like the geometric multiplicity and the algebraic multiplicity. I've avoided those details because for the application, most of those things will be handled internally by Python. So I've left them out. And besides, if we were to do all that, I think if I was to delve deep into the theory, we would not be this far into the course yet. We'll probably still be dealing with vector spaces up to now. So, ladies and gentlemen, let me wish you a good night. We resume next week.
Okay.